If you've been on the internet over the past month or so, you might have seen rumors that results from the new James Webb Space Telescope proved that the universe is much older than we previously thought. Now, if this were true, this would be huge news for cosmology, a total shift in what we thought we understood about the cosmos. But is it true? I'll give you a little spoiler, probably not. But stick with us, because in today's episode, we're going to dive into how we know our universe's age. It's about 13.8 billion years, by the way. And we'll talk about what this new paper is, and why we're so doubtful of its results. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper.
Today, we're talking about the age of the universe. To start off, let me clarify that when we talk about the age of the universe, we're actually talking about how much time has passed since the Big Bang. That's not to say that there was nothing before the Big Bang. In fact, we really can't know that for sure. But the age of the universe since it existed in the hot, dense state of the Big Bang has been measured with very high precision by cosmologists.
Modern cosmologists have measured this quantity, the age of the universe, to be 13.772 billion years, with a remarkably small uncertainty of about 0.02 billion years, or about 20 million years, plus or minus. Among cosmologists, this is not a controversial number. We all pretty much agree it's right on. Maybe it's a little bit high or a little bit low, but everyone I know would be absolutely shocked if it isn't about the right answer. But recently, a paper was published in a real scientific journal that's challenged this conventional wisdom, claiming that instead of being 13.8 billion years old, our universe is actually much older, about 26.7 billion years old.
Is this our first debunking episode?
Ooh. Some of our discussions of MOND are a little bit debunking, I think, but
this is one specific paper that's gotten a lot of attention recently.
Yeah. I think this could be considered our first debunking episode.
Very exciting.
All right, very exciting.
So before we get to debunking this new paper, let's dive into how we got this 13.8 billion year number that cosmologists today are so sure about. So it turns out there are a lot of different ways to go about measuring the age of the universe. And all of these different methods point to the same number.
Modern measurements of the age of the universe are based on a bunch of different kinds of techniques and measurements. Okay, so we're not going to go through all of them today, but I picked three that I think kind of capture the main essence of how we go about this.
So we'll start with the method that, while not the most precise, is the most straightforward to think about. And this method involves getting an estimate for the age of the universe by looking at the oldest star clusters we can find. Later on, our methods will get more and more precise, and with that, more and more complex. So let's start simple, with method number 1, stars.
The idea here is we're going to look at stars are in clusters. These are a specific kind of cluster of star cluster called a globular cluster. The important thing about globular clusters is all the stars in these things form at about the same time. So you're looking at a big group, maybe 1 million or something stars, all of which have about the same age. Stars evolve differently depending on their mass, and the masses of the stars formed in a given globular cluster will vary. There'll be some small stars, some old stars, etc. And slowly over time, the most massive of these stars are going to burn out. They're going to run out of fuel. They're going to either explode as a supernovae or just become cold, dead stars. In any case, they'll cease to show up in our telescopes.
This might be a little counterintuitive. Bigger stars burn out and die faster than smaller stars. So the bigger the star, the more likely it is to be quite young. And the smaller the star, the more likely it is to be older.
For example, if you take a 10 solar mass star, so a star that has 10 times as much mass as the sun, this thing will run out of fuel pretty quickly in 20 million years. So if you find a globular cluster with some 10 solar mass stars in it, it's a really young cluster, okay? Tens of millions of years old or less.
Which is short in cosmic time.
It's very short. Very short. That's like, a snap of a fingers in cosmic time. If you find a 2 solar mass star in a globular cluster, it tells you that globular cluster is like less than about 800 million years old. A sun-like star, one with 1 solar mass of mass, that will run out of fuel after about 9 billion years. So if you find a globular cluster with a bunch of sun-like stars in it, you can be pretty sure that this thing is younger than 9 billion years. And so on and so forth. So we can look at a bunch of these globular clusters, and we can look at the distribution of the masses of the stars and get a pretty good idea for how old they are. So when you do this, you find estimates for the very oldest globular clusters. Like some are younger, but the oldest ones you see in the universe have kind of estimates for their age, which are in the like 12, 13, 14 billion years, something like this. And that's roughly what you would expect given the uncertainties in this technique for a universe that is 13.8 billion years old. So, this doesn't tell you to 10% accuracy how old the universe is, but it gives you a pretty good ballpark estimate, and that estimate turns out to agree with our more precise determinations.
That means that if we one day discovered a globular cluster of stars that were all really small, half the mass of our sun, and there were no big stars to be found in the cluster at all, then that might actually be some good evidence for thinking that our universe is older than we think.
So one downside of this technique, or an objection the listener might be having, is like, okay, so we measured a bunch of globular cluster ages, and none of them are older than about 13 or 14 billion years old. But that doesn't prove the universe isn't older. Maybe the universe is older than that. And that's okay, sort of a legitimate objection. But there's really nothing about the formation of stars that leads us to think that this shouldn't have kicked in pretty early, as early as a couple 100 million years after the Big Bang. So I think that's pretty unlikely to be a big concern, although, for all fairness, it is a, logical possibility. I think of it as, maybe an archaeologist who wants to find out when the Roman Empire started, and they go and they look for coins with pictures of Roman emperors on it. And you find some from 26 BC, and some from 17 BCE, and some from 17 CE, and some from 114 CE, whatever. You find a whole bunch of these, and they span pretty continuously from 27 BCE to the end of the Roman Empire several hundred years later. And you might go, well, maybe there were emperors before that. These coins all suddenly appeared then, but maybe there were coins before that and you just haven't found them yet. And okay, that's logically possible, but it probably gives you a pretty reliable indication of when that empire started.
Right, it would be unlikely for there to be coins with earlier emperors, and we just never found any of them.
Right, especially when you find a whole lot of them from the first Emperor Augustus, right? Mm-hmm. Yeah.
And of course, you could have a Roman emperor that's not making coins.
Sure.
Maybe a reason that the universe would not make stars for a while.
And if there were a credible way to explain why the stars shouldn't have formed pretty early in our history, then that would be a legitimate objection. But we don't have any reason to think that.
Mm-hmm. Plus, we're going to get into, this is not our only way to determine the age of the universe.
If this were our only way, then I would be more open-minded, I think, of what the age of the universe really is. All right, let's go on to the second technique, and this is determining the age of the universe by measuring how fast the universe has been expanding over time. So this goes back to Hubble and Humason in the late 1920s, who measured that the universe is expanding for the first time. What they were able to do is by comparing the cosmological redshift of light from galaxies, which is how much the light is being stretched as it travels across space. They would compare that to the distances to galaxies to determine how fast the universe is expanding today. So that's just one number, but we not only have that number today, we have versions of that number from different points in cosmic history. So we look at things, billions of light years away. We see how much the light from those things has been redshifted. We look at things from 10 billion light years away. We do that, et cetera, et cetera, et cetera. And we can construct a curve that describes how the expansion rate of space has changed over time.
If you know how the expansion rate of space has changed over time, you can use that to calculate exactly how long it took the universe to expand from its compact state in the Big Bang to what we see today. It's a similar math problem to something like this. Say I give you a graph showing how fast my car was moving at every point during my drive from New York to Chicago. You can integrate over that graph to find exactly how long my whole drive took. That's the power of calculus. Similarly, you can integrate over that plot of the expansion rate and get how old the universe is.
When you do this, you get the same sort of answer that we get through other means, about 13.8 or so billion years. And the precision is something right around 10% or so. So just using the expansion history of the universe, you can confirm the picture you got with stars, but with a little bit better precision than stars can offer. All right, so let's talk about the third method. Like I said, this is going to be less intuitive and more technical, but also our most precise way. And among experts, the most reliable way we have to determine the age of the universe. So in particular, I'm talking about looking at the distribution of temperatures on the light that was released into our universe 380,000 years after the Big Bang that we call the cosmic microwave background. So we talked about this in some detail a few episodes ago. I think it was episode 66 when space was filled with music. And this was all about how sound waves, acoustic waves, propagated through the plasma of light and matter in the early universe, and how those sound waves gave rise to small temperature variations in this background light that we see in all directions from shortly after the Big Bang. And the details of those temperature distributions allow us to do things like measure what kind of stuff is in our universe and how much stuff there is, like how much matter, how much dark matter, how much atoms, et cetera, et cetera, et cetera. It allows us to measure the large-scale geometry of our universe. And for the purposes of this podcast, it importantly allows us to measure quite precisely the age of our universe. So when you look at this detailed pattern of temperatures, you can quite robustly, quite precisely, quite accurately extract this age. And that's where this number that we've been quoting comes from, this 13.772 plus or minus 0.02 billion years.
Exactly how cosmologists do this is really quite complex. But here's a quick overview just to give you a sense of what we're talking about. Different types of matter and energy will affect the specific shapes of the temperature variations in the cosmic microwave background differently. For example, dark matter will make things clumpier by gravitationally attracting matter together, but protons and neutrons may also increase pressure while doing that, so causing those clumps to disperse a bit too. So we can take the very precisely measured shape of the cosmic microwave background and compare it to all the possible densities that each kind of matter had in the early universe. That gives us a pretty good idea of what all those relative densities really were in that early time, and how it changed from then to now. In addition to all this, we know how much the cosmic microwave background has been redshifted before reaching us, because we can calculate with particle physics what frequency the CMB photons were released at, and of course we can see what we're actually measuring them to be. So from knowing these relative densities, plus knowing the redshift of the CMB, we can actually determine the Hubble rate, or the expansion rate of our universe over time. And from that we can calculate how much time has passed since the cosmic microwave background. So trust me, it's okay if you didn't follow all of that. We're trying our best to summarize a very complicated calculation. It involves data collecting, statistics, a lot of math, particle physics, and all tied together by general relativity, telling us how the universe expands, depending on what energies it contains. So the point here is really just that this is a very involved and extremely precise way to determine the age of the universe.
All right, so far, everything we've said has been super standard cosmology. This is stuff you find in textbooks. This is stuff you learn about if you take a course on cosmology at a university. And now we're going to depart from that. We're going to depart from this controversial paper that it's been peer-reviewed and accepted in a legitimate journal To my surprise, to some extent. But the author is this Rajendra Gupta, who's an adjunct professor of physics at the University of Ottawa. And he gets around this conclusion, or tries to anyway, by invoking two new elements. First of all, he introduces or reintroduces a notion known among cosmologists as tired light. This was proposed by Fritz Zwicky, the same guy who saw some of the early evidence of dark matter and galaxy clusters. It was proposed by Zwicky back in 1929. And the idea is that maybe light loses energy as it travels through space. So we already know that as space expands, photons get stretched, causing them to lose energy. This is what we call cosmological redshift. But Gupta argues that in addition to that, light is losing energy by another means, some unspecified way that light, just individual photons lose energy at a rate faster than implied by normal cosmological redshift. To be clear, there's no evidence of this at all. It's totally speculation, but he posits that as a starting point of his analysis. And then secondly, and there are a lot of Easter bunnies here, right? Okay, we're introducing a lot of weird stuff to make this conclusion work. He posits that the speed of light, the quantity known as the Planck constant, and the overall strength of gravity, or the Newtonian gravitational constant, all change with time. Again, there's no evidence of this. As far as we can tell, the speed of light and Planck's constant and the strength of gravity are the same at all times in all places we have ever been able to measure them. But he's going to speculate that they all change with time. Furthermore, one of the ways that we can tell that these things don't change very much is like we can look at, light from stars and at all sorts of distances and times, or even clouds of gas and other sorts of things. And we measure these emission and absorption lines that come with different kinds of chemical elements. And those are all the same in everywhere we look. Okay. So if I look at a cloud of hydrogen, in the modern universe, it absorbs light at certain wavelengths or frequencies. And if I look at hydrogen 1 billion years ago or 10 billion years ago, it absorbs and emits light at exactly the same frequency. So this hydrogen works the same everywhere, and all the other elements, best we can tell, do too. And by changing things like the speed of light and Planck's constant, you would expect to change these lines. So he's going to change them in a way altogether that coincidentally keeps these lines in the same place. Okay, so you can see this is starting to be pretty contrived. He's put in a whole bunch of stuff that we have no evidence for. He's arranged it just right so that the things we most easily observe don't get changed. But yet when he goes about doing this, when he makes all these assumptions, he can work out that the universe could be a lot older than the 13.8 billion years we normally cite. He finds that the data is best fit in his very bizarre, very weird model if the age of the universe is 26.7 billion years. One of the motivations that Gupta cites for this model of his is related to an episode we did of Why This Universe about the JWST telescope and their observations of very massive galaxies at high redshifts or in a relatively early universe. In that episode, we talked to my friend and colleague Mike Bolin-Kolchin, and we talked about this, what they call the early galaxy problem. Why are there so many big galaxies so early in our universe's history? Most cosmologists don't think this is ultimately going to be a problem. They think when all the dust settles and everything looks, when we understand it better, when the measurements get more clear, when the data gets more abundant, everything will be fine. But Gupta says, no, this is a real problem. And it seems that it suggests that our universe is older than we thought. Now, even if that were true, I think it would argue that our universe is slightly older than we thought. After all, these galaxies that we see with JWST don't look 26 billion years old. They look, a couple 100 million years older than they should. So like, it's like he's finding a problem of 10% and is doubling the whole thing to try to reconcile it. So I think this is a misplaced motivation personally, but all the same, he does cite that as part of his reason for doing this. So as I'll get into, and I'll describe some of the reasons in a little bit, but I just want to say up front that I think this paper is almost certainly wrong. And it's so wrong that basically everyone would have just ignored it and would have gone away if it weren't for like how it got amplified on social media and in certain corners of the just online media. It really exploded when there were a pair of tweets, one by Joe Rogan and one by Elon Musk. And these went out to, something like 10 million people and were retweeted something like 10,000 times. And for a while, if you just Googled the age of the universe, the thing that popped up at the top of the screen was 26.7 billion years. So this can actually, this is real misinformation. This can really, okay, there are kinds of science that the misinformation is more dangerous. Like if somebody tells you there's a 5G chip in your COVID vaccine that actually kills people, no one's going to get killed by measuring the age of the universe. But all the same, I think in this era of misinformation, it's important to call out a spade. And in this case, this is just, loud platformed idiots saying things that they don't understand for reasons I don't understand. Is that too harsh?
I liked that, though. Apologies if there are any diehard SpaceX fans out there. Dan might have gotten a bit excited. But it's true that misinformation is dangerous, and we believe we should call it out when we see it.
So I'm saying here that Gupta's conclusions are almost certainly wrong, which is probably a fairly charitable way of even putting it. And there's some really big fatal flaws. I'm not going to get into all of them here, but I'm going to focus on two that I think are pretty clear and easy to explain. The first has to do, again, with the cosmic microwave background. So we've measured the spectrum of the cosmic microwave background to incredible precision. When you see a plot of the spectrum of this light from the relatively early universe, if you see error bars on that plot, those error bars to be visible, they have to be multiplied by huge factors, usually several hundred. Otherwise, you literally can't see them within the width of the line that people use to plot a line on this curve. We've measured the spectrum so precisely that we have to say, if we had 400 times less precision than we do, this is what the error bars would look like. That's just incredible. We don't measure things that precisely very often in science. And when we do this measurement, we find that this light is described very, very accurately as what we call a black body spectrum. So black body spectra are the sort of thing that arise from a system that's in nearly perfect equilibrium. All the particles get to scatter for a long, long time, and then they come out in this very specific mathematically calculable spectrum that we call a black body. That is what we predict in the standard cosmological model, and that is what we observe to a very, very high level of precision and accuracy. But in a tired light theory, like Gupta's talking about, the spectrum of the cosmic microwave background would have been very different. So I'm going to try to explain why this is the case. So in standard cosmology, two separate things happen to the photons that make up the cosmic microwave background as space expands. First of all, the number density of the photons gets diluted just by the simple fact that the volume of the universe is getting bigger. So you have the same number of photons. The photons aren't going anywhere. Well, they literally are traveling, but the same number of photons at all times. So as the universe gets bigger, the number density of photons gets smaller. It gets diluted by the expansion of space. And the second thing that happens as space expands is that the individual photons that make up the cosmic microwave background get stretched as space gets expanded. This is what we call cosmological redshift. So I can compare the number density of photons to the average energy of photons and get a very specific prediction in the standard cosmological model, and that's what we observe. In tired light theory, the dilution happens in the same way, but the individual photons lose energy faster. So they will have, for the same number density of photons, will have a lower average energy. That is not what we see, and that is what has to be true in some sort of tired light theory. So I think we can just absolutely rule out any theory that has the kind of level of tired light phenomena that Gupta's talking about here, just on this measurement alone, just from the spectrum of the CMB. All right, so that's one reason. Another really compelling reason for why we can't take a theory like this seriously is that we already have measurements that are very sensitive to the quantities of speed of light, the Planck constant, and the strength of gravity, Newtonian constant. And we have measurements of these things at different places and times. And there's no evidence these numbers change. Best we can tell, all of these numbers are the same today as they were billions of years ago in the past. One particularly strong way we have measuring this, it uses a very weird phenomena most people don't know about. But it turns out that about 1.7 billion years ago, on the surface of the Earth, in a part of what is now West Africa, had a naturally occurring nuclear reactor. Okay, so there's just a bunch of uranium in the Earth's crust, and at this point, and there's less of it now because of radioactive decay and stuff. But at this time, there was enough of it, and there was a self-sustaining nuclear reaction that happened for a long time in this part of the world. People have discovered, or scientists have found, 17 separate sites in West Africa where naturally occurring nuclear reactions took place in this window of time. And by measuring all the characteristics of this, all the signatures that were left behind, we can measure a quantity called the fine structure constant. This is essentially the strength of the electromagnetic force. And that constant depends on the speed of light and Planck's constant. And it turns out that the fine structure constant is exactly the same then as it is today, to 1 part in 10 to the 16, at least, maybe less. So that means that the speed of light and Planck constant haven't meaningfully changed over the past 1.7 billion years. And this is a constraint that's billions of times more stringent than the sort of changes that Gupta's talking about. Gupta's saying these numbers are changing a lot with time, and that's just empirically false. We have really good and really empirically robust ways of saying nothing like that takes place in our universe. There's definitely a lot that we don't know about our universe. Cosmology as a, intellectual program isn't over by any means. We don't know what the dark matter is. We don't know what the dark energy is, or how it came to be the way it is. We don't really understand the first fraction of a second after the Big Bang. All sorts of open questions remain worthy of further exploration in the field of cosmology. But we do understand the broad history and evolution of our universe quite well, and with great confidence at this point in human history. If you tell me that our universe is 27 billion years old instead of the standard 13.8 billion years or so, that to me sounds like you're telling me that you have new evidence that the American Civil War started in 1706, based on some sort of letter you have or some sort of archaeological evidence. I know when the Civil War started. It started in 1861. Everybody knows that. So if you're going to try to convince me of something as radical as that, you really have to have a compelling argument. You have to dot your I's. You have to cross your T's. That's not what's going on here. We do know the age of our universe. We know it with staggering precision and accuracy. And I think we can just move on from there.
Hey, Why This Universe listeners, we've got a podcast recommendation for you. I Know Dino, the Big Dinosaur podcast. Studying dinosaurs can teach us about the prehistoric world, but also the world today. Migration patterns of dinosaur lineages tell us about Earth's changing continents. Climate models of dinosaur ecosystems helps us understand global warming. Studying dinosaur diets can even help show the link between plant and animal evolution. A new episode of I Know Dino comes out every week with new dinosaur discoveries you won't hear about anywhere else. You can find I Know Dino on Apple Podcasts, Spotify, or wherever you get your podcasts. Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.